Okay, so in the last lecture we have discussed the frequency spectrum of Fourier series, and in this lecture let us consider a few examples related to the frequency spectrum of complex exponential Fourier series. Suppose I take this waveform x of t and its value is a plus a and here minus a, and this point is t naught over 4 and okay, let's say t naught by 2 and this is 0 origin and time t. Okay, let me consider another waveform. It is time shifted waveform of that one. It looks like this. Like this it goes. So therefore it is a shifted version of x of t. So let me call this is x2 of t and this one is x1 of t. So this point is t naught by 4 and this point is minus t naught by 4. Then the waveform goes like this and so on. Okay, now in this waveform we have already worked out. So the Fourier series coefficient in this case is C, let me say Cn11. It indicates x1 of t is equal to minus j times 2a over n pi. Now the question is, what would be the Fourier coefficient of this waveform? So this waveform is x2 of t. So Cn suffix 2 of t. So that's what we want to relate x1 of t with the x2 of t. Okay. So you can see from this figure 1 x1 of t and this one is x2 of t. Figure 2. From figure 1, these two are essentially the same waveform. X1 of t and x2 of t are essentially the same waveform except for a shift in the origin. So the origin is shifted, that's all. In fact, x2 of t is obtained by advancing this a quarter period. Okay, x2 of t is obtained from x1 of t by advancing little bit to the left hand side. The relation between x1 of t and x2 of t is x2 of t is equal to x1 of t. You advance by quarter period t naught over 4. Suppose similar events are made to occur t naught 4 seconds earlier than the waveform x1 of t. In x1 of t, a rise from negative a to positive a occurs at 0. See, this point it is minus a and this is positive a. So negative a to positive a occurs at the 0 point. But in f2 of t, the same thing occurs at t naught by 4 seconds earlier. So this t naught by 4 seconds earlier. Okay, so this is the relation between x2 of t and x1 of t. So the whole thing is advanced by t naught by 4 seconds in x2 of t. Okay, so let's say the Fourier coefficient of this guy is denoted by Cn2. This 2 denotes x2 of t. So this is going to be, let me write down the formula. We know the formula is equal to 1 over t naught integral of 0 to t naught. Here x2 of t e to the minus j n omega naught t and dt. What is x2 of t? x2 of t is given here in terms of x1 of t. So 1 over t naught integral of x1 of t plus t naught by 4 e to the minus j n omega naught t dt. This is Cn2. Now let us rearrange this. In order to relate Cn2 with Cn1, let's make the identification that, let's say t plus t naught by 4, let's say tau, right? Here the lower limit is 0 and upper limit is t naught. When t equals 0, then tau equals t naught by 4, right? And then when t equals capital T naught, then tau equals 5 t naught over 4, right? T plus t naught plus t naught by 4, that is 5 t naught by 4. And next one is t plus t naught by 4 is equal to tau dt is equal to differentiate with respect to tau, so d tau. Substitute all these values in the above integral, then it is 1 over t naught integral of t naught over 4 to 5 t naught over 4. Now this becomes x of tau, x1 of tau e to the minus jn omega naught, here tau minus t naught by 4, right? T naught by 4 t tau, right? So in this again, if you rearrange, you will get 1 by t naught integral of t naught by 4 to 5 t naught by 4 x1 of tau. You rearrange this guy, multiply inside, e to the minus jn omega naught tau times e to the plus jn omega naught t naught by 4 d tau. Now after all, tau is a dummy variable, right? You can replace the dummy variable by tau t. Again, once again, nothing will change. 1 by t naught over 4 to 5 t naught over 4 x1 of t e to the minus jn omega naught tau, and again this is constant. Omega naught is equal to 2 pi f naught, and t naught is equal to 1 over f naught. Substitute there. So omega naught t naught by 4 is equal to 2 pi f naught, t naught is 1 by f naught divided by 4. F naught will get cancelled, and this becomes 2 pi by 2. Therefore this is e to the jn pi by 2 times dt, and this you can bring it outside. E to the jn pi by 2 1 over t naught integral of t naught over 4 5 t naught over 4 x of t e to the minus j omega n naught t and dt. And what is this? Don't you see, this is precisely the exponential Fourier series of x1 of t. So e to the jn pi by 2 times cn1, the left hand side cn2. What is cn2? The exponential Fourier series coefficient of the time shifted version of x1 of t. Okay, and this is exactly equal to cn1. Why? You are integrating over one period, t naught by 4 to 5 t naught by 4. So 5 t naught by 4 minus t naught by 4 is equal to 4 t naught by 4, which is t naught. So over one period. So and dividing by 1 its duration, and so it is obviously equal to cn1. So this is my relation between cn2 and cn1. Now if you look at this guy, this I can write cos of n pi by 2 plus j times sin n pi by 2, and its magnitude is equal to 1. Its angle of course depends on the value of n. Okay, if you take the magnitude of that, there will not be any change. Okay, so x2 of t is equal to x1 of time advanced version of x1 of t by t naught by 4, and its Fourier series coefficient Cn2 is equal to Cn1 times e to the j times n pi by 2. Now if you take the spectrum, see, as I said, this is a complex number. So complex number has magnitude and phase. Okay, if you take magnitude, then Cn2 is equal to Cn1 e to the jn pi by 2, then Cn1 times e to the jn pi by 2 and magnitude, and the magnitude is equal to 1. Therefore, the magnitude spectrum Cn2 is the same as the magnitude spectrum of Cn1 x1 of t. The magnitude spectrum will be the same as that of Cn1. Therefore, no change. So, if you plot the magnitude spectrum Cn2, then at 0 the value is 0, and at 1 the magnitude is 2a by pi. At 2 there is no value, 1. At 3 its value is 2a by 3 pi. Let's say this is 2a by 3 pi, and this is 4, and at 5 it is 2a by 5 pi, and so on. Similarly, in the negative side also, for minus 1, again 2a by pi. At minus 3, 2a by 3. At minus 5, it is 2a by 15. That's it. So the magnitude spectrum remains unchanged. Okay, so the magnitude spectrum as that of x1 of t. So the magnitude spectrum of Cn2 and the magnitude spectrum of Cn1 are identical. No change. However, the phase gets modified because of the introduction of e to the j n pi by 2. Okay, so instead of this phase at each component, you have an addition of n pi by 2. So originally my phase, if you plot it, recall from the previous lecture, it is minus pi by 2, then again minus pi by 2, minus pi by 2, like this. 0, 1, 2, 3. At 1 it is plus pi by 2, at 3 it is again plus pi by 2, at 5 again plus pi by 2. This is the phase of Cn1. Now if you try to plot Cn2, then phase angle of Cn2 is equal to phase angle of Cn1 plus the phase angle of j times n pi by 2. Okay, so that you need to consider in that. If you plot it, then it is going to be like at 1, 0, at 2 also it is again 0, at 3 it is going to be minus pi. Okay, and at 4, sorry, 1, 2, 3, at 4 no value. You can compute and you can plot it. It's straightforward. At 5 it is pi. So therefore this is the phase of let's say phi n 2. Okay, that is phase angle of Cn2, right? At n equals 0 dc. Okay, so there is no phase. 0 means frequency omega is equal to 0, therefore no phase angle. So phi n2 has nothing here. At n equals 1, it is minus pi by 2. So add that to another pi by 2, because e to the j times n pi by 2, right? When n is equal to 1, then what happens? Already have minus pi here. There is minus pi by 2. At n equals 1, 1 second. Angle of Cn2 is equal to angle of Cn1 plus angle of n pi by 2, right? Substitute n equals 1 here, then angle of C12 is equal to angle of C11 plus angle of pi by 2, right? Now C11 is this angle, pi by 2 minus pi by 2 plus pi by 2, so therefore 0. That is why you got 0 here in this point. Okay, 0. At 2 again, if you substitute 2, then it becomes pi. So add to that another pi by 2, so that becomes 0. So at n equals 2, there is no component to deal with. At n equals 3, because we are not interested in n equals 2, we have the component only at n equals 3. At n equals 3, then 3 pi by 2 minus pi by 2. So which is again pi. Okay, so this pi is again 180 degree, and this 180 degree you can as well say it is equal to minus pi, minus 180, plus 180 and minus 180 both are one and the same. Okay, and so on. At n equals 5, it is again minus pi by 2 plus 5 pi by 2. Then if you add together, then it is going to be like 4 pi by 2. 4 pi by 2 is 2 pi. 2 pi is equal to 0. Okay, so it like that you can keep on calculate. So so you have a whole series of angles 0 and pi alternatively, and this is the phase spectrum of that. So the conclusion we draw from this is, if you have a square wave, whether you put at the origin or somewhere else, the magnitude spectrum will remain the same. If you have a periodic function, the amplitudes of different harmonics or the ratio of the amplitudes of different harmonics will remain the same, irrespective of where you pitch your origin, because that is the fundamental property of the waveform, of how different harmonics can go together to compose the given wave. So the final conclusion is that the magnitude will not change, only the phase plot will change. The magnitude spectrum remains invariant under translation in respect to time, but the phase spectrum undergoes a change depending upon where you put the origin. Actually I did a mistake here. When n equals 4, what is the value? When n equals 5, minus pi by 2 plus pi by 2. Therefore at n equals 5, this is 0. I'm sorry. At n equals 0, we don't have any value. Again at n equals 7, then you will have another pi. So like that. Okay, this is my phase spectrum. Please, I did a mistake. Okay, so usually we are interested only in the magnitude spectrum, because we would like to know the relative proportions of the various harmonic components. Suppose you find the Fourier series for a given waveform x of t, and then you have many waveforms, like all are integer multiple of your fundamental frequency. Now we would like to know what are the relative proportions of various harmonic components, how their magnitudes are related. Therefore, we can say that magnitude spectrum is invariant under the operation of shift in the time axis. So when we took this example, we just shifted the time axis here. Okay, so just we are look at the waveform, we are shifting the time axis. So even if you do the shifting, there is no variation in the magnitude spectrum. Fine. So let me consider a second example. Example 2. Suppose the periodic function that we are talking about is 1, which is a periodic impulse train. I have impulses like this. Let me call x of t. Now it has a constant magnitude everywhere, like this, at discrete points in the time axis. 0, 1, 2, 3, 4, 5, and this side also -1, -2, -3, -4, and so on. These are magnitudes like this, right? Now how do you describe this impulse train? This is called impulse train of impulses. So each is of impulse delta function of unit magnitude. 1, this is 1, this is 1 unit, 1 unit, 1 unit, all are 1 unit magnitude. Okay, so now here x of t is a periodic waveform with one impulse sitting in each period at the center. So you can write x of t formally as it consists of a number of impulses. See, this one is, how do you describe? That is described by del of t. How do you describe this guy? Del of t minus 1. And this one, del of t minus 2. And this one, del of t minus 3. And what about this guy? Del of t plus 1. And this one, del of t plus 2, and so on and so forth. Therefore, your x of t contains del of t plus infinity plus dot 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 plus del of t plus 3 plus del of t plus 2, right, plus del of t plus 1 plus del of t plus del of t minus 1 plus del of t minus 2 plus del of t minus 3 plus dot dot dot, right. So and let's say the difference between 1 and 2, this duration is t naught, right. So instead of that I can say this is t naught, 2 t naught, 3 t naught, 4 t naught, 5 t naught, like that. And here this is minus t naught. Let us assume it's not nothing is wrong in this. Minus 3 naught and minus 4 naught, like this. Now here this becomes minus 3 times t naught, minus 2 times t naught. This is plus 3 times t naught plus 2 times t naught. Then this is t naught, del of t minus t naught, del of t minus 2 t naught, del of 3 minus t minus 3 t naught, and so on and so forth, right. So in compact form I can write this x of t as sigma, let me put a variable k is equal to minus infinity to plus infinity del of t minus k times capital T naught. So for each value of k there is an impulse, or you can let us consistent with the notation n times, here also you can put n. So for each value of n I have an impulse. Now what is the Fourier spectrum for this? You have to find out Fourier coefficients to start with, and this can be done with a surprisingly ease, because whenever we have impulses inside the integration sign, the integration becomes quite simple, okay, that we have already seen. So in this case Cn is equal to 1 over t naught integral of, let's say, minus t naught to 2 plus t naught by 2, then x of t e to the minus j n omega naught t. Now if you expand this, you are taking the limit from this point minus t naught by 2 to plus t naught by 2. So in this interval who is sitting? Del of t is sitting, okay. So in that interval your x of t is del of t. Therefore h is equal to 1 over t naught minus t naught 2 plus t naught by 2. You can take any other interval also, nothing is wrong. E to the minus j n omega naught t dt. And recall the properties of your impulse, like if you have x of t times del of t, or let me write f of t. F of t times del of t is equal to f of 0 times del of t. Similarly, here also you can write 1 over t naught minus t naught 2 2 plus t naught by 2 del of t times e to the minus jn omega naught multiplied by 0 dt. And anyway this is going to be 1. So this is 1 over t naught integral of del of t dt minus t naught 2 plus t naught. And what is the value of this integration? This is the area under the impulse. What is the area under the impulse? It is 1. Therefore your Cn is equal to 1 over t naught. Whether you substitute n equals 0 or n equals plus or minus 1 plus or minus 2 and keep on up to plus or minus infinity, but the magnitude is always, Cn is always 1 over t naught. It is independent of time, it is not reducing. Generally the Fourier series coefficients will coefficients value will be decreased when you increase the value of n, but here all are taking constant values. Okay, so that's what, when we evaluate the Fourier coefficients, it would be advisable for us verify the general expression for Cn. Now if you plot the spectrum of this guy, then you have like this. This is n equals 0, 1 omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on. This is omega naught. And here also all are impulses. Not impulses by this time. The strength is 1 over t naught. 1 over t naught, 1 over t naught, all are 1 over t naught. Even at n equals 0 also you have 1 over t naught. Like this. Spectrum is flat for all components and has the same value 1 over t naught. What about the phase? Phase, say your Cn is equal to 1 over t naught, and t naught is a real number, right? So plus j times 0 you can write like this. What is the phase of this guy? Tan inverse of, you can think a plus j times b, b by a. What is the b value here? 0. Tan inverse of 0 by 1 over t naught. So this is 0 degree. For all values the phase angle becomes 0 degree. So it's a very interesting result, okay, that we got now. You have a train of impulses of unit strength. Here if you look at of unit strength, all are unit strength. Okay, occurring regularly in terms of intervals t naught. From one sample to another sample, that interval length is t naught. Then the spectrum for that is flat here. If you look at the spectrum is flat, constant, 1 over t naught. They do not go down as n goes up. Generally the spectrum goes down, right? Initially it will be like this, then reduces, then reduces, then reduces, like it goes, it reduces generally. But here it is not decreasing as n goes up. They retain the same level. So impartial to the order of the harmonic, whether it is a second harmonic or third order harmonic. See, this is the fundamental omega naught. This is a fundamental component, second harmonic, third harmonic, and fourth harmonic. So second harmonic, third harmonic, fourth harmonic, for all ordered harmonics, the amplitude remains the same, that is impartial to the order of the harmonic. All harmonics have equal strength. All harmonics have equal strength. Now one can ask a question, why this guy has equal strength for all harmonics, whether you take 0 Hertz or omega naught radians per second or 2 omega naught radians per second, 3 omega naught, 4 omega naught, 5 omega naught, or you can take infinity also, it gives the same contribution. Why is that so? That is the question we need to understand. See, mathematically one can evaluate and one can get the result, but beyond that we need to think a little bit more. Why is that? It gives constant contribution or equal contribution for all frequencies, right from 0 to infinity. Why is that? Because in the time domain, if you consider, the impulse rises in no time, right? So suddenly it increases. So whenever there is a sudden jump, then there is a chance of very high frequency. Okay, it has all kind of frequency. So when you take an impulse and find out if you try to find out its frequency components, then it has all the frequencies, not only one frequency. Okay, so that's what it means by, you take a time function. If the time function slowly increases like this, then you have finite number of frequencies. Finite number of frequencies. But in reality what happens, you just shoot up from 0 to 1 in no time, suddenly you are increasing. We know the frequency is equal to 1 over time. Now what is the time here? Time is 0, 1 over 0 means infinity, therefore its frequency is infinity. It has a contribution from 0 to infinity. In all frequencies it has contribution. That's what the physical meaning is. Okay, now it will be very clear when we talk about continuous time Fourier transform, where we will find the Fourier transform of an impulse. Okay, so for the time being, let us understand up to this point. Let us leave it at that point. So we will observe that x of t equals a train of impulses. Look at here, this train of impulses again. In the frequency domain also, we observed a train of impulses. Therefore, the Fourier series expansion is x of t is equal to, general formula, 1 over t naught sigma n is equal to minus infinity to plus infinity. What is that? X of t. Am I correct? No, it's not x of t. It is Cn e to the jn omega naught t. What is Cn now? Cn is equal to 1 over t naught, and this t naught is displaced by t naught seconds duration. Okay, so this is 1. I'm sorry, why this 1 over t naught did I put? No, this is not as per the formula. There is no 1 over t naught. I'm sorry, let me write down. Let me write down the exponential Fourier series. X of t is equal to sigma n is equal to minus infinity to plus infinity Cn e to the jn omega naught t plus jn omega naught t. Now what is the Cn value? Just now we found 1 over t naught e to the jn omega naught t, and n goes from minus infinity to plus infinity. So this is the result, which is very compact and has a very nice look about it. So you have the summation from minus infinity to plus infinity of the impulses, and each impulse has the strength of magnitude of 1 over t naught, that is the magnitude. Okay. So this spectra gives us an indication how the various coefficients remain the same. Right, we have taken one extreme example of the situation where the spectra magnitude remains constant right through. So with this background, let's go further and construct another spectrum. Let me take a periodic pulse now. This example is periodic impulses. This is a periodic impulse. Let us consider a periodic pulse. That means it has some finite duration. Periodic pulse train, not impulse train, pulse train. That means you have the waveform like this, and let's say it is like this. Okay, let's say this is minus d by 2 plus d by 2, right? And let's say this point is t naught by 2. Maybe I'll take this point as t naught by 2. This point is t naught by 2 and this one is t naught. Similarly, this point is minus t naught by 2 and this is t naught, minus t naught, like that. So at minus t naught again I have one more pulse like this, and t naught again, hold on, like this, and this one is t naught by 2. This is a periodic pulse train, okay, with a waveform with the magnitude with magnitude A. That means what? A rectangular pulse repeats itself for every t naught second. The pulse has a width of d, that is d by 2 minus of minus d by 2, which is d. Okay, the pulse has a width of d and an amplitude capital A. Okay, so this is a periodic pulse train, and the duty cycle is on time. Duty cycle is generally defined by duty cycle is equal to on time. On time is pulse duration d divided by total duration. Total duration is t naught. Okay, it will last only for d seconds out of t naught seconds. Let's say this is my t naught seconds, and out of t naught seconds, only d seconds it is on. So this is a periodic pulse train and the pulse train. So let us calculate Cn for this. What is Cn? Cn by formula 1 over t naught integral of minus t naught by 2 to plus t naught by 2 x of t e to the minus j n omega naught t dt. Okay, now 1 over t naught, and in this minus t naught the range is from here, this is a range, and in this range this is amplitude, and these are the values minus d naught by 2 to plus d naught by 2. Therefore d by 2 to d by 2, minus d by 2 to plus d by 2, d by 2. What is the x of t value? It is a times e to the minus j n omega naught, and a is a constant. You can pull out the integration a over t naught integral of minus d by 2 to plus d by 2 e to the minus j n omega naught t. Okay, and by the way, this is the standard formula for what? To calculate exponential Fourier series coefficients. Now if you simplify this, you will get a divided by minus j times n. So simple integration, okay, minus j n omega naught t naught multiplied by minus 2j. Let me write down the direct result. In between I don't want to write. 2a times n omega naught t naught sine of n omega naught d by 2. Okay, so we can rewrite this slightly. Like in the denominator, you multiply numerator and denominator by d by 2 like that. Okay, so 2 times a times d by 2 times sine of n omega naught d by 2 divided by this whole thing n omega naught t naught. No, this t naught you can bring it here, don't put here, then this d by 2. Now this 2, that 2 will get cancelled, so ad by t naught sine of n omega naught d by 2 divided by n omega naught d by 2. Let me call this as equation number 1, and I put this Cn in this form because this function we have is of the form sine theta by theta, which is a well-known result in mathematical literature, okay, which comes up quite frequently in waveforms of this sort. So plot the spectrum corresponding to the sine theta by theta. Okay, let's fill ourselves upon some background information about the variation of sine theta versus theta, sine theta by theta versus theta. Okay, let us see how it goes. Now we know sine theta by theta, it goes like this: sine theta function, it is a function of theta. What about theta? It's a linear function, theta. Now multiply this and that, right? Not multiplication, sine theta by theta. Let's say here the value is 0. And this value is some non-zero. So 0 by non-zero, 0. And here the value is negative, and here some value is positive. So again you will get negative value. So if you if you do these two guys, in fact the function repeat is the negative side also. Then sine theta by theta looks like this, keep on reduces like this. So this is the sine theta divided by theta. If you divide by theta, then the amplitude diminishes. So we are dividing the waveform sine theta by theta. We can see that as theta increases, the amplitude of the oscillation decreases. Why? Because the theta is coming in the denominator. On the other hand, when theta equals 0, then both are 0 by 0. 0 by 0 is undefined. Okay, you have to take limit at theta goes to 0. That means you will get a limit theta goes to 0 at this point in the origin. I am telling you. Okay, when theta goes to 0, sine theta by theta becomes 1. 1 by 1, it is 1. Take derivative both in the numerator and the denominator. Like it comes in the form of 0 by 0 undetermined form. Take the derivative of the numerator, it becomes cos theta. Denominator becomes 1. Again now substitute theta equals 0. Then you will get 1 by 1, which is 1 in the limiting sense. So when you divide this sine theta by theta, you get a curve like this. So this is sine theta by theta. Again at every crossing region, like a sine pi, sine 2 pi, then it becomes 0. This is pi, this is 2 pi, 3 pi, and so on and so forth. So it starts at 1 and it will exhibit oscillations with a decreasing amplitude. If you trace the peak, then it is decreasing amplitude, and here also the amplitude is decreasing from this negative direction also. Okay, so both the numerator and the denominator are odd functions, like sine theta is odd function and theta also odd function. Therefore the ratio is even function. Okay, so that is why the function is symmetric now. Sine theta by theta is an even function. See, the same thing is repeated here also. Whatever you have here, the same thing is repeated here. Of course, I did not draw the figure properly, but it is an even function. Okay, so this is the variation of sin theta by theta. This function occurs again and again in Fourier series, Fourier transform, and subsequent chapters, especially in Fourier theory. So we would like to see the properties of this. Right, when theta equals 0, it is 1. Again it becomes 0 at pi, theta equal to pi, 2 pi, 3 pi, and so on so forth. That's what I marked here, pi, 2 pi, this guy is 2 pi, this one is pi, and this one is 3 pi, this one is 4 pi, this one is 5 pi, and so on so forth. Okay, now we got an expression that is similar to this type, sin theta by theta type. So Cn is equal to a times d divided by t naught sine of n omega naught d by 2 whole it is not in the form, sine of n omega naught d divided by 2, again n omega naught d divided by 2. It is in the sin theta. So the whole thing you can consider as a theta, and this also you consider as theta. However, we do not have continuous variation of theta because this n times omega naught is changing at discrete points. So we are interested in finding out the values at specific values of theta, which are given by the integral values of n. Therefore, the spectrum looks like this. Like this, then it's a power spectrum, right? Like this, to keep on reducing, and here also like that, like this. So this is the envelope of the spectrum. Let's say mod Cn. Negative loops are flipped, okay, become flipped over. So this is the envelope of your Cn magnitude, because once you take the magnitude, then the negative part becomes positive part, so it will not be in the denominator. See, actually it is supposed to be like this, but because of the magnitude it comes to the positive side. Now what is the maximum magnitude? This is going to be this maximum value. If you look at the, where is that expression, this amplitude, okay, so that maximum amplitude is AD over T naught. Okay, the spectrum of a periodic pulse train will have this type of character, and since this is a real quantity, this Cn is a real quantity. Real quantity, as far as the phase is concerned, we can say it is either 0 or pi. Therefore, the spectrum looks like a line spectrum like this for different values of n. Its envelope looks like this. This is a spectrum. Like this. Since the Cn quantity is real, we can plot only Cn, okay, by magnitude. So we don't have to plot the phase spectra separately. So Cn is real, it is either positive or negative. So that information can be given, and that information is enough. Since Cn is real, phase spectrum is not necessary. In fact, phase spectrum need not be separately plotted. Okay, now let us see how we can use these impulses in evaluation of Fourier coefficients of some general function. See, we have seen that the evaluation of Fourier series coefficient of impulse train is very easy, because 1 by T naught, its constant magnitude. Okay, calculation of Cn is easy, and its spectrum also very simple spectrum, all are 1 over T naught. We can see that, we have seen that. See, the coefficient is 1 by T naught and the spectrum is like this. So whenever you have impulses train, then its Fourier series coefficient evaluation is very simple, and its spectra also very simple, 1 over T naught, 1 over T naught, like that. So now let us try to use this impulse train property, its simplicity, to find the Fourier series of some other square waveform or something else. Okay, so the next topic is use of impulses in evaluation of Fourier coefficients. Fourier coefficients. Okay, so just to try to recall from the previous couple of lectures, like if you have a triangular wave like this, and if you differentiate, you will get a square pulse like this. What is the magnitude of the square pulse? Let's say A. This A is nothing but slope of this guy. If the slope is equal to A, then if you differentiate d by dt, you will get a square pulse. Again, one more time, if you differentiate, then it is increasing no time, there is one positive pulse, and here there is one negative pulse. So whenever you have a pulse like a triangular pulse, then if you differentiate, triangular becomes square, and again if you differentiate, square becomes impulse. Now why am I saying all these things? Because if you take triangular pulse, let's say x of t, if you want to calculate a Fourier series, then it is little more involvement is needed in this one. So you have a little time consuming job. For triangular waveform, periodic triangular waveform. Okay, fine, let me take square wave. Again, this also little time consuming job. Let's say this is time consuming job, and this is a little time consuming job. Time consuming process. But if you have train of impulses, then it is very easy. So that is the reason whenever you have a triangular wave like this or square wave, then you try to bring to an impulses. You differentiate 2 times or 3 times like that, and then bring back to Fourier series, bring down to train of impulses. For that impulses, we know it is very easy to calculate the Fourier series coefficients. Okay, so I would like to take an example where we make use of the impulses in the evaluation of Fourier coefficients, because again integration of this impulse becomes square pulse, integration of square pulse becomes a triangular pulse. So the next example is, take a triangular pulse. I will draw only one pulse here. Let's say this is increasing like this, and then again decreasing like this, and this also decreasing like this, and this point is minus t naught by 4, and this point is plus t naught by 4 and this point is t naught by 2 and this one is 0 crossing point is 1 second, this waveform is not in the proper way, I didn't draw it properly. It goes like this, let's say like this. Yeah, there you go. So now this is minus t naught by 4 and this is minus t naught by 2, and the 0 crossing point, this is t naught by 2 and this is t naught by 4, right? So let me call this is x of t. X of t can be written as sigma n is equal to minus infinity to plus infinity Cn e to the Jn omega naught t. Okay, now to evaluate Cn for this waveform requires good amount of computational effort. You have to spend a little bit amount of time to calculate Cn, then you substitute back here and all those things. But now let's see what happens if you take the derivative of this x of t. Okay, here the slope is constant, right? The slope is constant. If you take derivative of x of t, it results in a square waveform like this. So the square waveform will be, it increases like this, constant in this interval, then again comes down, then again it is constant and it goes like this. Okay, so this is a typical waveform when you do the differentiation. Let me call this as x2 of t. Okay, so that results in a square waveform. Again you take the derivative of this guy. Let me call this as x2 of t. Then if you take again derivative of this, from this point to this point there is a positive slope, and from this point to this point there is a negative slope. Similarly, from this point to this point there is a positive slope, and from this point to this point there is a negative slope, negative slope like this. Okay, so this is x3 of t. What is x3 of t? x3 of t is equal to x2 dash of t. What is x2 of t? x1 dash of t. Therefore x1 double dash of t, second derivative. This is the first derivative of x1 of t. So these are the relation between x1 of t, x of t. I'm sorry, let me say this is x2 and this one is x1, then correct. x2 of t is first derivative of x1 of t, x3 of t is second derivative of x1 of t. Now x1 of t I have given here. Now how do you find out x1 dash of t for this guy? x2 of t is equal to x1 dash of t, right? So you take x1 dash of t is given here. This is x1 dash of t, differentiate once. So that is equal to summation over n is equal to minus infinity to plus infinity. Cn is constant, you can keep it as it is. Then e to the j n omega naught t. If you differentiate, j times n omega naught t times again e to the j n omega naught t. Right? Now what is x3 of t? x3 of t is again one more time differentiate. So sigma n is equal to minus infinity to plus infinity. Cn jn omega naught squared times e to the jn omega naught t. Right? So let me call this whole thing as Tn. Right? So now what is the relation between Cn and Dn? Now Dn is equal to Cn times jn omega naught squared. Now if you calculate dn for this periodic function, now this is the dn, okay, dn for this periodic function having impulses, then we know dn and cn are related by this equation. So that is a plan of action now. So we will find the Fourier coefficient for this waveform. This waveform we know how the Fourier coefficients are related. Okay, therefore this point is if you look at the waveform, minus t naught by 4 and this one is plus t naught by 4. Okay, and this point is t naught by 2 minus t naught by 2 and this point is plus t naught by 2. By the way, what is the magnitude of this impulse? Now let us fix it. Okay, let me give that value also, how much it varies. So this waveform is magnitude is a, and this one is minus a, right? Therefore this is plus a and this one is minus a. So the total jump is 2a, and here also the total jump to down is 2a. Okay, and the slope is from minus t naught by 4 to plus t naught by 4, therefore it is a times t naught, sorry, a by t naught. Now you can know for this, if you still have doubt, you can write down the equation y is equal to mx plus c in that form, then you differentiate, you will get the slope. That slope is this a by t naught. You can easily find out that. Like it goes like this, we need to find the slope of this guy. That point is minus t naught by 4 and the magnitude is minus a, right? And it reaches plus t naught by 4 and the magnitude is a. X axis, I am sorry, I have written the other way. So you have a function like this, and this point is let us write minus t naught by 4 comma minus a, and this one is plus t naught by 4 comma a. Now you want to find the slope. Let's say x1 y1, then x2 y2. You know the slope formula. What is the slope formula? y2 minus y1 divided by x2 minus x1. What is y2? Minus a. What is y1? A. So minus a divided by x2 minus x1, minus t naught by 4 minus of t naught by 4. So minus 2a times minus 2 t naught by 4, right? So what is that? Minus minus will get cancelled. So what will happen? This is 2 will get cancelled. This is a by t naught. 2a by t naught, right? 2a by t naught. Two a by t naught, 4a by 2 naught. No, I am sorry. That is 4 times a by t naught. So the slope is 4a by t naught. So the height is 4a by t naught, and this one is minus 4a by t naught. Now what is the total jump here? If you look at from here to here, the total jump is 4a 4a by t naught minus of minus 4a by t naught. So this is 8a times divided by t naught. So that is the strength of this impulse, 8a by t naught, and this also 8a over t naught minus 8a, and this also minus 8a over t naught, and so on and so forth. Therefore in this interval we know the formula to calculate dn. Dn is equal to integral of 1 over t naught minus t naught by 2 to plus t naught by 2 x3 of t times e to the minus jn omega naught t dt. Now you take this minus t naught by 2 to plus t naught by 2, this interval. So in this interval I have two impulses. One impulse is this guy. What is that guy? Its strength is 8a by t naught del of t plus t naught by 4. Now here also I have one more impulse, this guy. What is the strength of that impulse? 8a over t naught del of t minus t naught by 4. So two impulses I have in this interval. So this is 1 over t naught integral of minus t naught by 2 plus t naught by 2 del of t plus 8a by t naught, t plus t naught by 4, then plus 8a by t naught del of t minus t naught by 4 times e to the minus j n omega naught t times dt, like this. Okay, so in this range of integration minus t naught by 2 plus t naught by 2, I have two impulses. Okay, so in this range of integration I have two impulses. This is one impulse and sorry, this is an impulse, therefore minus should come here. So instead of plus, then you will get a minus 8a. So you can take 8a times t naught outside, so it becomes 8a t naught square integral of minus t naught by 2 to plus t naught by 2 del of t plus t naught 4 e to the minus j n omega naught t minus 8a divided by t naught square integral of minus t naught over 4 to t naught over 4, then del of n minus t naught over 4 e to the minus j n omega naught t and dt. Now we know the result. What is that result? Whenever you have a function like this, like x of t times del of t, that is equal to x of 0 times del of t. Recall that property, time shifting property. X of t minus okay, so x of t times del of t minus t naught, then this is equal to x of capital T naught times del of t minus t naught. Recall this property. X of t times del of t minus t naught is equal to, like that you can write. Same formula you can substitute here. Let's say this is your x of t, then this is your t naught, so this value will come here. So 8a over t naught square integral of minus t naught over 2 plus t naught over 2, this is del of t plus t naught by 4 e to the minus j n omega naught. Instead of this t becomes t naught by 4 minus 8a over t naught square integral of minus t naught over 4 to t naught over 4, then del of t minus t naught by 4, then e to the minus j n omega naught minus t naught by 4. This minus also comes here times dt. Now this is a constant you can pull out of the summation. Okay, so 8a divided by t naught square e to the j n omega naught t naught by 4 integral of minus t naught by 2 plus t naught by 2 del of t plus t naught by 4 dt. What is this? This is area. Area is equal to 1. Similarly, minus 8a by t naught square e to the plus j, here minus and here plus, jn omega naught t naught by 4 integral of minus t naught by 2 to plus t naught by 2 del of t minus t naught by 4 times dt. Again this integral becomes 1 because area under the unit impulse is 1, right? So you have these two guys, 8a divided by t naught square, this is common, you can take it outside, e to the minus jn omega naught t naught over 4 minus e to the plus jn omega naught t naught divided by 4. So somewhere I think I did a mistake, some minus sign is missing here and there. Okay, so just to look at this derivation somewhere, I think this will be minus and this will be plus. I have done a mistake somewhere else, just try to find out. So this is equal to, maybe you can multiply 2j by 2j both in the numerator and denominator, right? So therefore 2 times 8 16, j 16 times a over t naught squared multiply by, this is sine, so sine of n omega naught t naught by 4 becomes pi by 2, so this is sine n pi by 2. Therefore your dn is equal to j times 16a t naught square sine of n pi by 2, then Cn is equal to, we know the relation between Cn and dn, right? Jn omega naught the whole square, right? Dn divided by Jn omega naught the whole squared. So this is, what is dn? Dn is j times 16a divided by t naught square sine of n pi by 2. It's fairly mechanical procedure, just do it, minus n squared omega naught squared. So minus j times 16a divided by n squared omega naught squared multiplied by t naught squared times sine of n pi by 2. This is Cn. Therefore Cn is equal to minus j for n odd, okay, odd n, minus j 4a divided by pi squared n squared, then minus 1 whole to the n minus 1 by 2 for odd n, you can write like this, and 0 for even n. So that is the Fourier coefficients for the original triangular waveform, okay, and recognizing that Cn is equal to an minus jbn by 2 from your trigonometric Fourier series, then you can write this bn is equal to 8a divided by pi square n squared, then minus 1 whole to the n minus 1 by 2 for odd n. You can get back this, just to compare now this guy and this guy, so you'll get 8a by pi squared n square minus 1 like that. Okay, so an is equal to 0 and bn is equal to 0 for even n. So what about C naught? C naught also 0. Okay, C naught has to be separately evaluated, but in this case 0 because the average value will be 0. So other Cn had already been obtained. So finally your x of t is going to be 8a by pi squared sine of omega naught. You know the formula, right? Before that, let me 1 second. Cn is given here. This is my Cn. Cn, let us substitute C1. What is C1? Substitute n is equal to 1. Then it becomes 1 minus 1, 0. So that becomes 1. So 4 minus j times, let us wait, Cn is equal to minus j 4a divided by pi squared n squared minus 1 whole to the n minus 1 by 2, right? That's it. So this is the given expression. Now what is x of t? X of t is equal to n is equal to minus infinity to plus infinity, then Cn e to the plus jn omega naught t. Now let us consider n equal to minus 1 and minus 3. Here we assumed n takes only odd values. Here let us consider only for minus 3 and minus 1, plus 1 and plus 3 in this expression. You substitute in different values, like c minus 3 is equal to minus j times 4a divided by pi square, and 30 square is 9 pi square, right? What is c plus 3? C plus, again if you substitute here 3 minus 1, 2 by 2, 1, so minus into minus it becomes plus, minus 1, 2 minus 1 divided by 2, right? Sorry, 3 minus 1, I am sorry, it is missing. Let me write down neatly. C minus 3 is equal to minus j 4a divided by 9 pi squared minus 1, 3 minus 1 by 2, that is 2 by 2, 1 minus 1, this minus and this minus will get cancelled. Therefore j times 4a by 9 pi square, c minus 3. Similarly you can calculate c plus 3. C plus 3 is equal to what is that? It is just opposite of this, minus j 4a divided by 9 pi square. Similarly you can calculate c1. C1 is equal to, I think it is 4a by pi squared something, right? So similarly c minus 1 also you can calculate. If you substitute all the values in the above expression, then x of t is equal to 8a over pi squared sine of omega naught t minus 8a over 9 pi squared sine 3 omega naught t plus and so on, dot dot dot. Okay. So if you have a constant term here, when you take the derivative, I mean, see, this is my waveform like this. Okay. Now if you have any constant term, then what will happen? Constant term, when you take the derivative, the constant term disappears. Therefore a DC term get lost in the square waveform, right? If you take a square waveform, the DC term will lost. Therefore a DC term get lost in this waveform. Let's say this is x2 of t and x1 of t. Therefore the DC term you have to calculate from the original function, not from the derivative function. Okay. So rest other than DC term you can calculate from the derivative terms, like this, you can calculate from here, Cn and all, where n not equal to 0, but C0 should be, we should calculate from this waveform only. Suppose if you have any constant term here, that constant term will be lost once you take the derivative, constant term disappears. Therefore a DC term get lost here in this expression, DC term will be lost, and here also DC term will be lost. Therefore the the DC term in the original function has to be separately evaluated, because that information is lost when you take the derivative. So C naught in this case has to be separately evaluated. You cannot obtain from this information from the Fourier series, like x double dash of t is equal to sigma n is equal to minus infinity to plus infinity Cn times Jn omega naught the whole square times e to the Jn omega naught. Okay, from this you cannot get C naught. Why? Because you have taken 2 times the derivative. Once you take the derivative, the constant terms will disappear, where the C naught is the constant term, area. Okay, now what other terms can possibly get lost? If there is a constant term in the, in this expression, then also it is lost, the second waveform. Okay, therefore C naught get lost and has to be separately evaluated from the original waveform x1 of t. Okay, so this example illustrates how the Fourier coefficients can sometimes be evaluated by taking first or second derivative and making use of function which has only impulses. So whenever you have some triangular function or square function, then don't try to calculate the Fourier series, because it takes a considerable amount of time to evaluate. Okay, it will become very lengthy calculation or lengthy derivation. Mechanically it is little more involved. So in order to reduce the amount of time, what you do, you first take the derivative and again take derivative until you reach a function, until you reach a function which contains only impulses. Because calculation of the exponential Fourier series coefficients for an impulse or series of impulse or train of impulses is very easy. Okay, so let me stop at this point.